Ready? Hello, everyone. Welcome to this session this morning. So we have a special session. So two speakers this morning. So the first speaker is Giacomo Roberti, will be followed by Alex Dvorčić. So Giacomo is a postdoctoral researcher at Northumbria University. Was until less than a year ago a PhD student at Northumbria with Gelash. So I was doing lots of amazing work on around the topic of Soliton gases. So the title of the talk is here. So enjoy your talk.
Thank you, Antonio, for the kind introduction. I'd also like to thank the organizer and the Institute for the nice program, and also the Simon Foundation for partially sponsoring my stay actually with the program. So the work that I will present today is joint work with Thibault, Gennady, Alex, and Pierre Stefan Colli. And we will deal with the numerical realization of solid gases. The work that which the presentation is based is now on archive. We put it on archive last week. So we heard a lot of talk about solid gas. I just this week Alex finished his two-part seminar on spectral theory in solid gas. But I will start with a small recap anyway. So when we talk solid gas, we are using, we think of the definition introduced by Zakharov about an ensemble of interacting solitons with random distributed velocity, amplitude, and position. Zakharov introduced this concept in the framework of the KdV equation, and in particularly for a rarefied soliton gas. Subsequently, Gennady developed the spectral theory for the dense soliton gas for the KdV equation, and 2 years ago, together with Alex, again, Gennady and Alex developed the spectral theory for the focusing NLS equation for the equation for soliton and Ritter gas. So Alex explained in this two-part seminar how you derive the spectral theory, starting from a finite gap setup and taking a thermodynamic limit with the bands shrinking and so on. And we end up with a true nonlinear dispersion relation. This equation can be massaged a bit to get rid of the sigma, and we get a continuity equation for the density of state. The density of state represents density of soliton in both the spectral plane and the physical space.
So question here. This is KdV, right?
Yes, okay. Here I'm bringing the formula that I'm presenting now is KdV. The talk will be centered mainly on KdV. I will give some result later.
What is gamma plus?
So gamma plus is the support on the spectral plane where the bands is my super band.
Yeah, but it's in which is it?
Okay, is the positive.
Okay.
It's real. Yeah, it's real. It's positive. Yeah. We turn it positive. And we have an equation of state that describes essentially where S is our effective velocity. So it's the correction to the free velocity of the free soliton due to the interaction with the rest of the gas. If we look at the nonlinear dispersion relation, are not very nice and easy to solve. But if we want to solve them, we can take a special limit when sigma goes to 0, and we have what we call the soliton condensate. And in this case, the main contribution to our equation is the integral part, that is the interaction term. And this is actually the densest possible gas that we can do. In the formalism, if you look at the formalism of Ken and Manuela Marzo, what they define, I think, as deterministic gas. Essentially, we get rid of our randomization. And if we look at the simplest case possible, with our support is a single band, we get a G0 solution, and this is the density of state. It's known as a pi distribution for the area. So at this point, what are the challenges we have? First, it will be build this have an expression to construct this Soliton gas, and we have different approach. We saw Ken gave a seminar 3 weeks ago, or repeated that approach. We can think about multi-phase solution and Soliton solution to build an explicit solution of our gas. And I think Alex, Marco, and Bob are working on connection between different approaches for the construction. But now in this talk, we are interested mainly on how numerically we generate them. And what we develop is an algorithm to approximate, to generate an n-Soliton solution to approximate our Soliton. So as I was saying, all of the formula that I brought down so far are for the KDB. So let's, before jumping in the algorithm itself, to work on KDB, we consider KDB in this form, and actually we consider simultaneously two different forms of the KDB equation with different signs in front of the nonlinearity. This is obtained just
It's 5T.
sorry?
It's 5T, right?
Yes, sorry. Yes, there is a touch. Right. Yeah, right. So we have plus minus in front of the linearity, and we can switch from one equation to the other simply to a symmetry, sending psi in minus psi. We have our scattering problem, and in particular, when zeta is complex, we have a discrete point of the spectrum that corresponds to solitons. So what we want to do is we want to build a solution for the KDB equation when we have a set of parameters eta, hopefully as big as we can. To do so, we implement an algorithm that relies on a Darboux transform. The Darboux transformation is an iterative method to create a hierarchy of solutions, and the transformation itself does not act on the solution, but on the Joss function corresponding to the solution. So starting from a Joss function of a solution psi, through the Darboux transformation, we generate a new Joss solution of the new solution psi of our equation. And considering simultaneously these two forms of the KDB equation, we can simplify the algorithm, but we generate, essentially, we jump from a solution of the equation plus to a solution of the equation with minus. But this is not really a problem because we just need to change the sign and we got the solution of the equation that we want. So how it works, the algorithm? First, we need a SIG solution, so our initial condition for which we will build the hierarchy. And this initial condition we will consider the void solution, for which we know everything. Everything it means that we can write explicitly the Joss solution of our solution. Then we have our set of parameters eta and non-constant p, and we order them from smallest to biggest. And then we start turning the machinery. The machinery is composed of our Darboux transformation in a Polex function. And we have this matrix Pn that is actually a projector matrix that is this non-variance form. And actually the solution, we can rebuild the solution starting from our Joss solution J through the matrix Pn. And actually this is the recursive relation to get the n solution of the KDB. equation from the n-1. So now we can, okay, before going through the gas that we can generate, we will spend some time on the definition of our norming constant. So our norming constant has this form, and where x0 naught represent, if we generate a single Soliton solution, x0 naught will represent the position T0 of the initial condition of the center of the solid. But once we add more than one soliton, this interpretation is loose meaning, and we need to say that the x0 naught is the average position of the soliton between minus infinity and plus infinity. So if we build our asymptotic solution at t equal minus or plus infinity, we have an asymptotic position xn plus minus that corresponds to our x naught plus or minus, if we are asymptotic in plus infinity or minus infinity, of all the phase shift. So in this way, at each soliton, let's say, is symmetrized around x naught for t equal plus and minus. Once they are ordered from faster to slowest and slower to fastest. And last thing is multiprecision. So if we just take and start running our machinery, we will very soon encounter some problem related to round-off error, because we are summing, adding big, small exponential. We are adding recursively poles in our solution, and so the round-off error of our algorithm, our numerics, will add up, and very soon we have completely non-physical object. So to solve this problem, we follow the work by Gelash and Giacomo. They did it for NLS, but translated to JETP perfectly, and we implement some arbitrary precision library. And to give you an idea, essentially we need a number of digits of precision that is 1.5 times the number of solitons that we want. So if we want to create a 100 soliton, we need 150 digits of precision, roughly. So it becomes clearly quite.
Yeah. So what you're saying is 150 digits is to capture the whole set of solitons over the x-axis from minus whatever.
Yeah, but also if you have mainly problem at the border, so you can imagine that if you are just focused on the center, you maybe can get away with less digits of precision.
But how far can you go in time? Is it because I suspect that more digits if you go far in time?
So we never went, I guess so, but we never went far enough to see if this has an effect. But yeah, at some point we
the associations you see at the borders invite
Lisa.
So okay, Lisa, is this the noise?
Yes, this is the numerical artifact to the round-off error that comes out of the. So now that we did, we introduce the algorithm. Okay. So
When you say what precision?
Sorry?
Libraries like library C++?
Yes, this one C++ is a standard tools library that and there is, there is both for real or complex, because okay, this is for KDD, it's everything real, so it's easier. Once you go in NLS, you need the precision complex number, and so it actually there is.
So what I was saying.
Okay, this is just a random realization of a Soliton gas with this one The spectral parameters are distributed according to the Phys distribution, if I remember correctly, but the norming constant and the phases are nothing. They are spaced like 1 over n, I guess, something like that. But yeah, this was just an example. So instead, if we go in the what we actually were interested in generate is the genus zero condensate. So as we introduced before, we have our density of state, that is our Phys distribution. Actually, we can invert it to get the position of the soliton given the total number of solitons that we want. And then we fix the phases, the one that the initial phases, all to 0. In this sense, we try to make them as compact as we can. And what we observe is the formation of a box. So we have some order effect due to the finite size of our object and a lot of oscillation. This is done for 200 solitons. Now, if we zoom in, we won't just look, we will look just at the center of our object, and we compare how we behave changing the total number of solitons. So what we observe, we have, so the dashed line is the realization for 100 solitons, and and the continuous line, black line, is realization for 200 solitons. Take care that there is a zoom also in the y-axis, so we are very close to the constant. Yes.
Go to the previous slide. So what defines the
Well,
compared to what we were showing?
Just the box.
Just the box.
yes. Okay.
What defines the size? So if you throw more solitons, the size will grow.
Yes. So the size of the soliton grows roughly as pi. So we have here, we have the density that is 1 over pi that essentially represents our spatial density. And the size of the box is essentially n times pi. We can say roughly each soliton will occupy a pi space in our realization. And actually just yesterday we did some very quick numeric to check. And as n grow, we get closer and closer to pi. So to this next. And and we are comparing, okay, thanks. And we compare our solution with the constant graph, with a constant solution, because actually in the work that we publish, we are publishing. We can show that we have the Phys distribution generated probability 1, the constant solution. And here are the error between the two, so the exact solution in our solution. Another thing that we can do is like we have time, so we can generate the solution to at each time that we want. And what we do here, we generate the output. We write it, I think it's 3.40 with the same realization. And we can observe the formation of a dispersive wave on the right of our Riemann problem. And on the left, we have the formation of a rarefaction. And actually, this solution, I believe, all the theoretical prediction. Next step is what will happen if we slightly dilute our condensate. So it's what we call diluted condensate. So we introduce a parameter C in our density of state, and this will translate essentially in a essentially we distribute our initial phase not anymore in just a single point, but we have a small support in which we uniformly and randomly distribute our initial phase.
How is LS related?
Okay, LS and C are related. Now I'm not sure. It should be rho S. Rho S would be equal rho 1 C, where rho is the density of the physical space, so it would be C over pi, and rho S is the density in the phase space, so it would be number of solitons over L. I'm not sure I'm going like this by memory. The body comfort. Okay. So what we observe is that essentially we break our very nice flat solution and we generate a lot of oscillation. And this is for a value of this dilution constant very small. We are 0.97. So we are very close to the condensate, where C is equal 1, but our solution is produce a lot of oscillation. So another result that we can extrapolate from the equation of state that tell us about the effective velocity is that we can show that for condensate there are some parameters, some of the soliton in the condensate that will actually move backward. Even if we are in KDB where the free velocities are all positive, we can observe negative effective velocity. And I don't know if you can see this is the zoom of the spatial-temporal diagram of a diluted condensate with, I think, 200 solitons. And if we look, we can see this slightly clearer trace, lighter trace that we can say it's a soliton, in the sense that if we follow this trace up to the moment that the soliton, the gas will break down and we will observe the separate soliton, we can follow this trace up to the soliton that will come out of the condensate. And here you can clearly see that as a negative velocity. Here we have comparison, just as a recap of G0. So we have condensate, so we have the initial box, and with the noisy one that is all noisy. Intermediate step in which we have rarefaction wave and dispersive shock, and the correspondent version when we have some randomness and some dilution, and then the asymptotic state, essentially, when all the solitons are almost okay. It's not asymptotic yet because they are not completely separate. And analogous for the diluted one. And also here you can, I think, guess the trajectory of the soliton going backward in the point. 5 minutes. 5 minutes, okay. So maybe this part of it goes like faster. We can do the same with genus one solution. It means that now our support, our gamma is no more a single band, but we break it down in 2 different bands. The eta are the position of the endpoint of the band, and then our density of state is as this form. We can invert it no more analytically, invert it numerically to generate the position of the poles to generate the gas. But what we create is this kind of object. Again, we have some border effect. And again, if we zoom in and compare for different number of solitons, this is the error and the difference that we have from the exact nodal wave, because we have a conjecture that actually the genus one condensate will correspond to the nodal wave solution for the KDB up to a phase. Because before we were constant, here we have an oscillation, so we will be up to a phase. And again, we can compare between the perfect condensate, so when C is equal 1, we introduce a dilution parameter, and we have also here some noise formation and so on. Also here you can observe, maybe even clearer, the soliton going backward in the special angular diagram. And here we have comparison of like 3 times the evolution. And in the intermediate time, you can see, you can observe a refraction wave, a condensate of G0. You have generalized refraction wave, two-phase solution, and so on. And here is the asymptotic state due to the gap in the velocity, because we have 2 bands and a gap in the middle. We will have a gap in the velocity, so the 2 family of solid state will separate. And was there a question? And we can do also genus 2 condensate. I didn't write the density of state because it will start to be a bit excessive. Here also to under soliton, we have a 2-phase solution. We can observe the heating between the 2 solutions. And again, we can zoom in. And this time we compare with the 2-phase solution of KV equation that we obtain solving using the Glovin system and the trace formula. And again, the comparison is very clear. Here we will increase the number of phases for which the comparison is done. Few last very fast slide I have on Soliton gas. So in focusing NLS complex, we have a complex parameter. The algorithm is essentially the same, but we have complex parameters, so it's simplified less. We have 2 conditions, Soliton gas if our C solution is the void again, and just solution and constant. But in this case, we can also have breeder gas. This means that our C solution is no more the void, but it's the non-zero background. We have a different just solution and so on. And from this, I will just present 2 results, one published by Gelash and collaborator on the modeling of the modulation instability for focusing NLS with the dynamics of a random phase Soliton gas of G0. And okay, the picture probably won't convince you, even if they are very close to each other, but in the work they present also some statistics, compare the statistics, PDF, power spectrum, autocorrelation, and they perfectly match. And for the breeder gas, instead, I will just do some zoology and present some results we publish. Here it's just we're generating, we want to test some spectral theory of particularly the equation of state for the breeder gas, and we could generate what we call Kuznetsov activity and very good gas, distributing our spectral value in the spectral plane where we would imagine the single object would be the specific kind of thing. And okay, I think and
We have time for 1, maximum 2 short questions.
otherwise there are videos.
Any questions?
I have a stupid question just about the coastline. Why not we use in this occasion for KDB at least the standard classical formula for any Soliton solution? Well, they need to block the table.
Okay.
Just technical reason for that.
Yes. So when you do that, you need to evaluate this determinant. It's in condition, but it's also more complex. I think is so. This is you have complexity n squared. It means how it grows the time when you compute it. I guess that for the determinant is n cubed, and so is lowest. Is lower.
Just to be able to see it in the sort of calculation.
Yeah. It's for the numerator.
Any more questions? So in the meantime, let's thank the speaker again.
Yeah.